Yeah. It, so is this all of the graduate students or some purport, like?
Usually the incoming graduate students, we give them the opportunity to miss a few, and so they're not all of them.
It's all first year electrical and computer
First
engineering.
year, yeah. And then also since we put this on the web, I have allowed them, if they cannot be here in person, to tell me that they're gonna watch it and then give me the
Okay.
but they have to tell me.
So it's on the web live or it's on the web recorded? Okay.
But hopefully for next year it's gonna be live streaming.
Okay.
So let's start. Today we have a very interesting lecture about the work done in a very special facility. And as you know, the overview of target diagnostics at the National Ignition Facility. I will ask Professor Charles Khan to make the introduction because he has been very familiar with the facility, with the work of the group and the two individuals who are presenting today. But I just want to say that's going to be a very interesting presentation, and I would like to thank you for being here.
Thank you, Professor. Okay, today we have two speakers tag teaming on this. Dr. Robin Benedetti, and also our own Arthur Carpenter. Laura got her degree from UC Berkeley, and Arthur got his degree from UC Davis. And they are in different capacities working with the National Ignition Facility to look at very fast phenomena, and I won't talk anymore. I'll let them do it. So I should say, if you're interested in what they talk about and are interested in co-ops or internships or possible graduate study or employment down there, you can come talk to me.
Good afternoon. Can you hear me all right? So we're talking today about the National Ignition Facility at the Lawrence Livermore National Laboratory, and this is sort of we're going to do an experimental tag team presentation, in part because that's a good representation of how we work at NIF. I'm a physicist, Arthur is an engineer, and typically we work physicists and engineers together on how to make these really complicated measurements. So I've been told that despite the fact that we're just around the corner in the greater Bay Area, not a lot of people know very much about the National Ignition Facility. So here is the Just the Facts Ma'am page. The Lawrence Livermore National Lab is one of the Department of Energy research laboratories, and the National Ignition Facility is within that. It's the largest laser in the world, and it has been built to study inertial confinement fusion and materials in support of stockpile stewardship. And let's see, so the where is Livermore, California. That's one mountain range east of San Francisco. And we started building in 1997, and the first integrated experiments were performed in 2010. So we are almost 10 years into using it as an experimental research facility. Fusion might someday help enable abundant, safe, clean energy. And it also supports the stockpile stewardship program, which helps enable not doing nuclear tests in Nevada and the Pacific. So this is our map. San Francisco is over here. I can see this one better. This is the Lawrence Livermore National Lab, and the National Ignition Facility takes up a large corner of the laboratory. So that was the who, what, when, where, why. Most of this talk is going to be about the how of NIF. So what we are exploring is the physics of fusion, which is pretty conceptually simple. We are looking at deuterium, which is an isotope of hydrogen, and tritium, which can fuse to create a helium atom and a neutron and 14 MeV of energy with a pressure and temperature and confinement. So that's what we need. We need to get these isotopes of hydrogen to high pressures and temperatures. We are using inertial confinement. The most common example of fusion is gravitational confinement. That's in the stars. So they're fusing, and they are held together by the fact that they're large stars. So they're gravitationally held together. Tokamaks, you may have heard of, they are keeping your plasma together with magnetic confinement. We're going to use inertial confinement, which is that we're driving an implosion and the momentum of the material holds it together for long enough for our reactions to happen. So NIF was built to study ICF. It's a very large facility to explore very tiny targets. And we need diagnostics to know what we're doing. So a lot of our work is building diagnostics. This is the number of diagnostics we've built at NIF to date. We can continue to commission them, and this is a large collaborative environment where we work with many national labs and universities to build and design each new instrument. So I've talked about this a little bit. So deuterium is a proton with a neutron. Hydrogen is a proton. Tritium is one proton with two neutrons. If you get them together, they will make a helium. We take a very small plasma of these deuterium and tritium, try to get them to high enough pressure and temperature to make this reaction. We make energy in the form of the neutron, which is traveling at almost 20% the speed of light. And then we lose energy by, if the neutrons fly away, thermal conduction, X-radiation, expansion. And what we're trying to do is create a plasma that has more energy created than lost. So there's this Lawson's criteria that says if you can get this quantity pressure times confinement time higher than this black curve, Lawson's criteria, you will be able to get more energy out than the energy losses. So that's our goal, is to try to get up here at this high pressure, hold it together for long enough. You'll see that long enough means like 100 picoseconds. And hot enough to get more energy out than we lose by other methods, and eventually more energy out than we put in. So how do we do that? In NIF, the X radiation is generated by a UV laser that hits the walls of something called a holram, which is a little empty cylinder, to compress a capsule. So this is our 10-meter laser chamber. And in the tiny center of it is about 1 centimeter of an empty cylinder. And inside that is 1 millimeter of a plastic capsule. And this is where our fusion is going to go on. So the way we're doing it, in inertial confinement fusion is it's just a totally different color on screen. Sorry. So the laser comes in, shines on the holram, to the walls of the holram. The holram gets hot enough that it emits X-rays. Those X-rays fly in to heat up our capsule in what's called ablation. So we burn off the plastic on the exterior of the capsule, and that makes like a little rocket. So all the interior of the capsule rockets in, imploding at very high speed, hundreds of times faster than a bullet. And it's going so fast that as the implosion comes together, the material stagnates, gets very hot, very high pressure, creates this fusion burn. That's our goal. That's how it works. Here's a video. It all happens in 20 nanoseconds, so 10 to the minus 9 seconds. So the lasers come in, they hit the wall, that starts ablating the capsule implodes. All of that happens in 20 nanoseconds or less. A lot of experiments are 10 nanoseconds now. So that's what we're trying to do at NIF.
You hear me? All right. Okay, so I get the easy part. I get to show off how big the building is and, and how big the laser is. But we will both talk about some of the diagnostics that we work on. So, sorry. Better? Okay. So I started, I was here in 2007. So 10 years ago, I was in the same lecture. And I never knew that this place existed. And I think it's one of the coolest research facilities in the world. I mean, I do enjoy what I do. but it's also the biggest laser, the most energetic laser, and it's really a feat of engineering. So let's get to it. This is a nice, pretty picture where nobody's parked in the parking lot for some reason. So NIF is quite big. It's 3 football fields, if you will. Sorry, no Davis here. But most of this is laser. So this whole back here is the laser bay. So you got 200 yards of lasers, and then you have some switch yards turning all the beams around, and then they go into this chamber back here. Huge capacitor banks. It was designed in the 90s with the best technology they had at that time. And then it took 15 years to build it. So here's kind of a picture of the laser bay. So beams come down this, they get amplified. It's a multi-pass system. 20 nanosecond pulse, it's 20 feet, speed of light is 1 foot per nanosecond. So you kind of have to scale everything on that, that size and amplifying something that's very precisely shaped. The beam, the pulse starts out at picojoules, and it comes out at megajoules, so 10 to the 18 amplification throughout that whole system. The target chamber was also another big feat of engineering, kind of made like a volleyball. It's got 4-inch thick aluminum and has 200 ports in it. So it's basically a big spherical chamber so that we can get all the lasers in. And all the round ports are so that we can take measurements of what's happening in there. So this is kind of a cutaway just for scale. You can kind of see a person down here and a person up here. And then all the lasers coming in from the top and the bottom hemispheres. And then this is before we've installed everything. Kind of just showing you how it's 3 stories tall just around the chamber. And people are working on these final optics assemblies. So this is, the light is generated as 1053 infrared light, and then it gets converted with nonlinear optics into the UV 351 nanometer. That couples better to the gold hole ROM than the system than it would if it was just infrared light coming in. And then here's the inside of the chamber. Again, for scale, we have a little personnel lift that allows work in there. We vent the chamber maybe once a year to remove and install things that have to be inside the chamber. They filmed Star Trek in here. This is what the actual chamber, the actual warp core looks like. It doesn't look like what they showed in the movie. But again, I think we're trying to get the scale in. You got 3 football fields, and it's all going into 10 millimeters. All that energy in there. And we basically use a laser because you can control the pulse shape of a laser better than you can control the delivery of energy of any other way. So accelerators, Z-pinches with big electrical currents, we have so much more control over it. The contrast ratio is 80 to 100 dB. That there's just no other way that you can do that. These kind of experiments that need to have that kind of precision. Yeah, that's kind of a reference for what was in the center of that chamber held on that target positioner that you saw out there. And some of the other things in that previous slide, let's go back real quick. So this is the target positioner. This holds a target. This is a camera that looks at the target. We'll talk a lot about these. And then this is actually a camera that comes in after the shot and looks at all the beam lines. And then this is another diagnostic. So there's a lot of things that kind of come up close, and that's one of the challenges in designing this whole thing and operating it. So once we get the energy onto the inside of the whole ROM, we got this rocket ablating everything, the surface, kind of driving this in. This is a 2 millimeter diameter. It's a small capsule. CH, carbon hydrogen, is basically plastic that's doped a little bit. And then you grow a DT isolator. So a hydrogen layer is grown in situ with a little fill tube, and then it's basically put out into the center of the chamber. The shrouds that cover over this to keep it, because it's at 18 Kelvin, and right before the shot, these open up and all the lasers come in, and everything's completely automated. So here's kind of the starting diameter shrinks down, if everything's going well, to a few hundred microns or less. And then it looks like that if you do a simulation that takes several weeks on a supercomputer. It's kind of a 3D hydro simulation that shows instabilities and mix and other kinds of phenomena that we expect to see based off of what, if you start with an ideal condition. And our job is to kind of diagnose what actually happened. How close are we to the simulations, and how close are we to actually getting ignition, which is generally defined as 710 to the 17 neutrons into 4 pi. 14 MeV primary neutrons. So we got a little video. Pardon the slightly dated music, but this kind of flies through the laser system and then shows you what's happening for everything we've described.
Shot director, ready for shot. Starting countdown for shot on my mark. 3, 2, 1, mark. Clock is running. 5, 4, 3, 2, 1, shot.
So everything's happening in less than half a second, a tenth of a second from the countdown. The flash lamp's firing, pumping the neodymium YAG lasers. This is the master oscillator room, so that's when that perfectly shaped pulse is coming out. So it starts with one pulse, it gets amplified out into 48 quads, and then it's injected into the main laser, and it goes through a multi-pass system that amplifies it up. So like I said, it started at a few picojoules. We got to get it up to a megajoule. So we have fast optical switches called Pockle cells. That can switch this laser back out of the multi-pass system and out into the switch yards. So all 192 beams have to arrive within 10 to 100 picoseconds. So a lot of the optical path matching and the measurements of getting that all timed in together is actually very critical to get uniformity inside that whole ROM. Otherwise, if one spot is not as bright or it's not as timed the same as the others, you'll impart an instability that will ride the whole implosion in and cause it to not work, basically. So it's been converted to UV light here, and now we're talking in nanoseconds. So we've heated up the whole ROM, generating X-rays, starting to blade the capsule. Driving it in. So clear as mud. So this is an actual picture of what the shot looks like. So if you took a normal camera, a CMOS camera, and you put an ND10, so that's 10 to the 10 optical density, you would see that, and it still saturates the camera. And these are pictures of some of the diagnostics that you see plasma being generated off the surface. So I'll hand it back to Robin to talk a little bit about the physics and some of the diagnostics. So we have 100 different diagnostics. We certainly can't talk about all of them. So we're going to talk about one from each of the different types of measurements we're trying to make, but it's by no means a complete overview, which would not be possible in 1 hour.
Okay. Thank you. So basically, that all happened so fast. You know, you can't just look at it and say, oh, how did it look? Let me go in the lab and check on it. So we need diagnostics at every point along the experiment to know how we're doing, how close we are coming to ignition. So we've sort of divided this up into 4 kind of categories of things we're interested in. We need to know how the laser worked. How well is the energy delivered to the target? And did we damage the laser in the process? Then we want to know how well did we start the implosion? How well did the laser couple to the capsule to start the implosion? That's the laser converting to X-rays, converting to kinetic energy of the capsule. Then we want to know how well it stagnates. How uniformly did this implosion crash into itself, essentially? We're converting kinetic energy to thermodynamic energy, pressure and temperature and density. And then if we do that well, we finally need to know how many neutron reactions did we get? How many fusions did we see before the target exploded? So that's the inertial confinement. The momentum of the implosion is holding it together until it explodes. And we are just trying to hold it together long enough to get enough energy, and to get as high a nuclear yield as possible. So we're going to go through each of those sections briefly, talking about some of the kinds of measurements we make, and with one sort of case study in each, if we get to it. So in this first section, diagnosing the laser, how well is energy delivered to the target? Now, in all of these little slides, I think it's really interesting that we use a lot of different kinds of detectors and a lot of different kinds of instrumentation put together to make a diagnostic. So I have a little code up here of sort of common things that you might know about: CCDs, microchannel plates, street cameras, lasers, optics. And this is a code. So for each of these diagnostics, I've sort of coded which elements are used to make that measurement. So in this question of how well is the laser delivered to the target, so the lasers come in and we do some calorimetry measurement to know how much energy comes in. But we want to know, well, does some of that laser energy actually go back? A lot of it does actually get scattered back up the beam line. So if the world's largest laser is NIF, the world's second largest laser is the energy that's scattered back and re-amplified. So that can do quite a bit of damage, not to mention it puts energy not into your target. So we're interested in measuring that. And we have a backscatter measurement here where we actually have street cameras looking back up the laser channel, and we're measuring the amount of light versus time that comes back up. We're also interested in knowing how well the laser coupled into the whole ROM. So this is the whole ROM right here at the center of the target chamber, and we have several diagnostics that look from the side of NIF up at an angle through the hole where the lasers went in. So this one, the static X-ray imager, it just is taking a picture of where the lasers hit the wall. So this is the lasers. You can imagine you're looking like up the side of a tube. And then we also have a spectrometer that also is looking up the whole entrance hole that's measuring the temperature of the wall as a function of time. So this is how well we're getting the laser into the target. And then our case study in this is the final optics damage inspection. So after, like I said, we are really concerned about laser going back up, scattering back up and damaging the laser. And in addition, NIF is operating sort of at the peak of everything. We had to engineer new laser glass just to make it work, but we're still operating at very high fluences, so we can do a lot of damage to the optics. So after every shot, we send in this camera, and it actually takes a picture up each beam line, each of the 192 beams, to see if there's damage. So we can continue to use these damaged optics if we repair them. So we send in the photi to look at each optic. Then each photograph is automatically, all of the defects are noted, counted, tracked. When there are too many, we have to actually take the laser glass out. Everything's done in a clean room in a bodysuit to repair them. And then so here's a picture of damage, and there's a bunch of subsurface cracks, and we're really concerned about the laser going down those cracks, being amplified. So we can mitigate that by just etching a cone around that damaged site so it becomes smooth, uniform glass again. We do that with the laser, and so here's an example of the cone after the repair. And this is really important because optics replacement and repair is the limiting factor. We do as many shots as we have laser glass to replace and repair. We do no more, and some weeks if we do damage, we do fewer shots. So we're really limited by how fast we can do that repair. And it turns out that this is a case of where we at NIF have used the fact that we're at a large national laboratory with people doing many other kinds of research. So we've collaborated with the computing groups at LLNL to use deep learning algorithms to assess this. So here I have some still photos after the repair of cones of repair. So these ones on the left, the repair is incomplete, they're still damaged. These ones on the right, the repair is complete, and we can use the glass again. Can you just look at those and tell which are which? I mean, you might guess, but you might guess wrong. And it turns out that even if you train someone to get it right, they have to watch the video of the whole repair, so that could be 5 minutes. They have to be trained, and they only get it right 91% of the time. But now that we have sent the deep learning image analysis on the task, we can actually get it right 98% of the time, or the computer gets it right 98% of the time. and all they need is the final image. So this allows us to speed up our optics repair and replacement quite a bit. Next quick section, diagnosing the implosion. This is how is energy transferred to the capsule. How well do we know that? So this is what we're trying to do, compress the DT gas. Again, we're using many different diagnostics to try to make this assessment. We use a streak camera interferometer called VISAR to measure the velocity of the shocks as they pass through the capsule. We use an X-ray streak camera called SPIDER to measure what we call bang time. This is at the very peak of the implosion. All of our fusion reactions happen, and also a lot of X-rays are emitted. So we measure when that happened, and then we back out, just using like Newton's laws. If we know when it struck, when it stagnated, we can figure out how fast it was going to get there. So that's a streak camera that's mounted here. This is the top of the target chamber, measures X-rays versus time. And then we also have a gamma reaction history measurement that, again, it's measuring when we had the most nuclear reaction, using that to back out how fast we made the capsule go. And then the case study I wanted to talk about is streak cameras. As electrical engineers, many of you may know much more about this kind of diagnostic than I did when I started. It's basically, it's a tube, but we start with the photocathode that converts X-rays to electrons, and then we focus the electrons down the tube using electron optics to get them to an anode where they feel a voltage ramp. So the voltage redirects them to our detector at the back, and as the voltage changes, where they are directed changes. So you end up with a picture of space in one direction and time in another direction. So we're looking at a streaked image of X-rays in this case. And for this dim inserted streak camera, we have an X-ray streak camera very close to the target. And the way we use it, so here's our whole ROM picture. We make X-rays on the outside of it, kind of like an X-ray of your broken arm, by diverting two of the lasers to a foil. That makes X-rays, and the X-rays are sent all the way through the capsule, through the whole ROM, through the capsule, and then they escape, and we put our X-ray streak camera over here. And so if we do this during the implosion, we take a radiograph of it, and what you can see is this is time, 2 nanoseconds in this direction, and we actually look at the edge of the capsule. Where it's thickest on the edges, it's impeding the radiograph, so we have a shadow. And just by looking at this shadow versus time, we can see how fast it's imploding. So we can just take this image, measure radius versus time, take the derivative, get velocity versus time, and now we can figure out how fast the capsule is screaming into its implosion. The third characteristic we're looking at is stagnation. How close are we to the Lawson's criteria? What pressure did we get to? What temperature did we get to? And it's increasingly clear that we're really concerned with how symmetric the implosion is. If it all came in at one time, we get a nice round burning plasma. But if it didn't, we get something that's not round. So we use those same measurements that we did for bang time to measure how long we've confined things. So this spider that I talked about before, it measures X-rays versus time. The center is when the implosion happened, but here we can see the width of X-ray emission and see how long we held it together. And then, so we can also measure the symmetry with the neutrons, and this is a bunch of activation detectors that actually, neutrons come flying out. They create unstable reactions. We have to take them to the counting facility and count how fast they decay back into stable cases. But then I'm going to talk a little bit about some of our imagers. So we're interested in taking images of the X-ray emission. It's very hot, so it's emitting X-ray. And I'm not going to talk about, but we also are interested, we can collect images with the neutrons as well to see how symmetric the reaction, the implosion is. But for this talk, we're talking about high-speed X-ray imagers. In particular, when we built NIF, we just put together like a very nice new version of some not very new technology. So we use pinhole optics, which are hundreds of years old, and we then project pinhole images onto a detector that uses a microchannel plate. That's the newest element. It was developed in the 80s. And then CCD or film. So all of the pieces are not really new, but this is a workhorse diagnostic to collect X-ray images. We use it on almost every shot. But there is a lot of room for diagnostic improvement in the field of X-ray imaging. So again, so this particular camera uses a microchannel plate, which is like an X-ray to electron converter, and then an avalanche photo, like a photodiode. And then we coat the microchannel plate with microstrip lines and send a high voltage pulse through them. And only when the voltage is on is the microchannel plate a camera, is it amplifying the electrons. So that acts as a traveling shutter. So only when the voltage is on are we collecting an image of the pinhole projected optics. So each pinhole makes an image that turns out to be at a different time. The time that we record depends on how fast the pulse propagates. So in our 34 millimeter camera, we can get about 1 nanosecond of recording time. But each shutter speed, each image collects for as long as it takes the electrons to fly down the pores of the microchannel plate. That's about 100 picoseconds, or 40 picoseconds if you make the microchannel plate really, really thin. Still, it's an incredibly fast camera. So this is a video of a bullet striking a wall. This high-speed camera is 500,000 frames per second with a 2 microsecond film resolution. Our camera, so here is our video of our implosion. This is the target getting smaller and then exploding afterwards. This video is 10 billion frames per second with a temporal resolution of 100 picoseconds. So it's 20,000 times faster than your off-the-shelf high-speed camera. But is it good enough? Our whole implosion takes less than a nanosecond. So maybe we need resolution better than 10 picoseconds. We can't make the microchannel plate faster, but we can spread the images out in time. So think of this like when you look at a bunch of spinners at the start of the race, they're all together, but they have different speeds. So by the end of the race, they're well separated. We're going to do the same thing with X-ray images using a technique called pulse dilation. So we have our incoming X-ray signal, and it hits a photocathode, which converts it to electrons. So those electrons, the ones that came in first, are in front. The ones that came in last are in back. And then we apply voltage ramp. So this spreads them out. The electrons that arrived first have see a higher voltage, so they are accelerated more, they go faster. The ones that came in later go slower. And then we put them in a magnetic tube drift space, and they just drift along. And by the time they get to the end, they're so well separated that we can measure them at 10 picoseconds resolution. So this is our new-ish camera at NIF with 10 picoseconds resolution. And you can see that it's in this giant lead box because the whole environment is very difficult. But with this 10 picosecond resolution, we can see features in the implosion that we couldn't see before. So it turns out there's stuff happening as fast as 10 picoseconds or faster. So all of these images on the top are 200 picoseconds of an implosion at 10 picosecond resolution. And all these ones on the bottom are our old camera that with only 100 picoseconds resolution. And you can see that they see sort of the same general features. The whole thing is getting smaller. But if you look with 10 picoseconds resolution, you can see there's a lot more motion that happens a lot more quickly. So it turns out the faster we look, the faster we see things. So there's a lot there for us to look at. But that's the old technology, and now Arthur's going to tell you about the future.
No. Okay, So pinholes are old. Probably the first pinhole use was somebody thousands of years ago poking a hole in a leaf or something like that to look at an eclipse. And you get a whole bunch of images at different points in time, but they're not really the same image. Can we do better than that? That's kind of a question we ask ourselves all the time. And are there optics that are better than a pinhole? Certainly in the visible spectrum there are. In the X-ray spectrum there are as well, called multi-layer mirrors. You can have a grazing incident of an X-ray and actually focus it down. But you can only fit so many of these in there. They're like $1 million each, and it's a very difficult endeavor. So what if we could take more than one image in that space back here? Well, we can't really use a microchannel plate and a CCD. You got to use something better. And basically, one of the things we've been working on, and part of the reason we explained all these older technologies is we need something better to replace them. So you have to kind of understand what the needs are and what the old technology was, and then to be able to prove that you could do better in the future. So we have a new sensor that is built by our partners at Sandia. So we're a national lab, but we collaborate with a lot of other institutions. Sandia has a fab and has a whole bunch of crack ASIC engineers, and they've been working for more than 10 years on building a solid-state camera that can take images on the same scale as that microchannel plate-based imager, but the whole thing at once. And so they've been doing this, for the last few years. They've had some success, and we're using some of these in NIF, but they have to use pretty advanced technology for them. Granted, it's still 350 nanometer technology, so it's old, 1995 CMOS technology. But if they design a pixel, and then they design a separate detector array that they can bond to it or hybridize, they're able to have cameras that are faster than anything else that is out there for a full frame imaging, not interlacing, not giving up active area. And with that, you can couple that to an advanced X-ray optic and take multiple pictures one after another. So how does this work? Because this is this is electrical engineering and computer engineering lecture. Let's talk a little bit about how they built this, because it's kind of the forefront of technology right now for solid-state detectors in NIF and other facilities like NIF. So they based it off of a standard CMOS. So you're familiar with CCD. CMOS is like a 1-pixel CCD, randomly accessible. So they have this backbone of the readout and the control underneath everything, and this is kind of your camera pixel that might be in your cell phone. And that's great. You can do it in a kind of a monolithic single wafer kind of device, but it's not going to be fast enough. You're going to be diffusion limited. You're not going to be drift limited. You want to go faster, you've got to put an electric field on it. So as I mentioned, this hybridization process, you can bias a photodiode on top. You can hybridize it on and then bias this up and get to your velocity saturation. And you can put different types of detector technology here, and a plug with Dr. Hunt. We're working on doing that now. So this is kind of active research, cutting edge stuff. So if you bond these two together, you create this hybridized detector where you can customize the readout circuit, which is an ASIC, basically a readout integrated circuit designed for a camera. So if you're familiar with switch cap digitizers, this might make a little bit of sense to you. But inside this IC or this ROIC, there's some digital logic, and there's the pixels being switched in. So to run this, you have to configure it. You set up your integration times and some of the other basic stuff. You have a high-speed oscillator that turns on right when it gets a trigger. So we've configured it. We've given it a trigger. Now you're getting some of the pixels are turning on. You have a reset circuit that has to turn off. You get charge generated in here, flowing into the capacitor, so it can be stored later for readout. And then you can switch it off. And then later in time, like a nanosecond later, you can turn on another capacitor and store another images from the same pixel later. And this has really enabled a whole new field of diagnostics. So we've, like I said, we would read it out later with a off-chip ADC. So we built a camera. So the sensor is pretty R&D level. It doesn't have integrated ADCs or anything like that. So we and other UC Davis grads designed a camera system to run this, and it was a pretty big feat of engineering, I would say, even though it's relatively small. But a 14-layer board, 5 or 6 ADCs, 1,000 components, 4,000 nets, and it pretty much worked the first time. And we were able to put this out in IF, and we were able to characterize the sensor. So this is the digital world here. It's on and off in 2 nanoseconds, and this is what it actually does. But of course, 500 million frames per second, as Robin said, is far too slow. So let's put one of those pulse dilation things on the front of it and put it into one of these air boxes that we put close to the target and take some images. And this is a reflective X-ray optic. So this is like a crystal that can reflect X-rays back off of it and back up this line of sight. And so this just got commissioned. This was, this is kind of a new technology that's actually been thought about for a long time, but they never had a sensor that could do this. And so it's kind of opened up a new world. So now your 2 nanosecond frames are back down into the 40 picoseconds, and it can certainly go faster. One of the last big things that we wanted to cover here was how many neutrons come out of NIF, and how do we measure that. A neutron has got mass, so it has a velocity. So we use a lot of these time-of-flight detectors. You get them late. The slower neutrons have lower energy, so you can make a spectrometer out of that. We also use GRH and GCD. So these are gas Cherenkov detectors that were mentioned earlier. They convert gamma rays into electrons traveling faster than the speed of light in a gas, and you collect that optical signal. And then this is something called the magnetic recoil spectrometer, which I'll talk about a little bit in the next slide, which is also a neutron spectrometer, basically. But I want to pause here a little bit because I'm going to put out an engineering challenge based off of this physics kind of simulation data. So here's your kind of primary 14 MeV neutrons. This is the spectrum. This is what's called the downscatter region. So these are neutrons that bumped around in here before they came out. They had lower energy. And we really want to measure this part of this signal really accurately. And if you flip this in time, a time-based detector will get this kind of a signal. But if you look at the scale, this is a log scale. And you're talking about 3 orders of magnitude, and you need precision better than that, probably another order of magnitude in precision. And you need you're going to have variation in the amplitude of the signal. You don't know what you're going to get, because sometimes the target will work and sometimes it won't work so well. So you need 10,000x dynamic range, which is a really hard problem. And just a single shot digitizer that can do that. So I'll talk about that a little bit. Well, how we do that now and can we do better is kind of a question I'd ask this audience. So here's this MRS. This is an absolutely calibrated device. It takes neutrons hitting a foil. They scatter and kick out protons or deuterons, which are double protons, that get bent by a magnet. They hit a foil. The foil leaves tracks. We etch that. We count it. No electronics whatsoever. The neutron time of flight is a little bit fast, a little bit more electronics. You have a cable, a photomultiplier tube, which just takes an optical signal and turns it into an electrical signal with some gain. And then we look at it on a scope. And so here's kind of this data from that neutron time of flight diagnostic. So here's real shot data, and here's this is the impulse response of the system. So you have to calibrate that impulse response really, really well so that you can back out what is a signal from your cables or from your scope versus actual physics. And that's a real problem. That's a real challenge. To take that kind of data, to get that kind of dynamic range, what we do now is we have a scintillator. So this just gives out optical photons as neutrons come in. We look at it with 4 different channels that have different attenuators in them. They go through tube-based oscilloscopes that have 6 gigahertz bandwidth and 11 effective bits, because they take a CCD picture of a phosphor trace, and then a bunch of digital scopes. This is the only way that we can do this now. Could we do this with a single channel? Is there a digitizer out there that could do that? It has to basically meet these kind of requirements. We have to be able to measure this width of this peak. We have to measure this downscattered region. And so these are kind of physics requirements, and this is why we talked about we're partners, we work together. But I have to understand the physics that's going on, and I have to think about new technology that can solve this kind of problem. And I have to be able to go to companies or to lecturers and say, can you get me a digitizer with 2.5 gigahertz bandwidth with greater than 12 effective bits? And so far, nobody's been able to do that. So if you know something, please come talk to me. And then another idea that we're working on is to make the MRS time resolved. So instead of just counting tracks going into a foil, could we put this onto some kind of a detector? Could we do some pulse dilation technology so that we can look at things on the picosecond time scale? And that's basically in the works right now. So we can stretch it and we can separate the energy spectrum spatially. But do we have a technology on the back end that can read this out efficiently? The first order thought is, okay, let's just have a bunch of anodes. So there's a bunch of pieces of metal hooked up to a scope with some amplification from microchannel plate. That will probably work, but your number of bins for your energy spectrometer, is kind of defined by how many scope channels you have and how many anodes you have and how close you can get them. Can we do something better than this? Is there modern technology, modern detector technology that can do better? So we're kind of looking at custom SIPMs and other types of detectors that might be able to replace this. And this is also generally not rad hard. I haven't even talked about that, but making everything rad hard in the facility is important. So kind of in conclusion here, and give 5 minutes for questions at least, we're at a point where we're really trying to look for new ideas, new innovations to be able to take this kind of simple equation and break it down to how well are we actually doing at achieving fusion in a lab. And we need to diagnose this. We need to come up with new ideas. We need your help out here. And every year we're putting on new diagnostics. NIF has postings out there right now, and internships and stuff like that. And it's a very interesting place to work. You get a little bit of physics, and then you get to bring in new ideas, deep learning. You get to bring in a new technology. So with that, I'll kind of close.
Okay, that's an excellent question, and I meant to point that out. Our experiments right now, we are getting 5 and sometimes 6 keV temperatures, and we have not really crossed into the energy gain, but we're close. Yeah,
It's a runaway process, and that's kind of the $3 billion question, right? When are we going to get ignition? We make progress on diagnosing it, then we can come up with solutions to the problems. There's a lot of instabilities caused by this thing they call the tent with 35 nanometer film that holds the capsule in place, imperfections in the surface, imperfections in the laser drive. All of these things kind of limit our ability to get to the right pressure and temperature and density needed. And right now, our max yield is about 210 to the 16. Total neutrons, ignition is 710 to the 17. So that's kind of where we are.
Yeah, it's important to remember that it is a runway process. As we get closer, the reason that we're so interested in this downscattered problem is because it represents like how much dense stuff you have around your plasma that keeps your plasma confined, and that's in like the very low energy part of that neutron spectrum. But as we have more and more ROR, we get sort of faster and faster because we end up heating up those neutrons, and then they contribute to the yield as well. The more we can hold them in, the more it runs away. So even though we've sort of been marching up in nuclear yield, neutron yield, now that we think we've hit to a place where we're starting to be a little bit self-heating, and we are marching up in bigger steps. So we think we're like right on the cusp of it being the runaway generation.
Also curious, has anyone gotten results that are better than it, or is that
No.
No.
This one and then the other.
Wait,
Compared to a tokamak, what's the advantage of inertial confinement fusion? Tokamaks are using magnetic fusion and kind of a CW process, continuous wave. And I'm not that familiar with tokamaks. They can confine the fusion for a certain period of time, and you can do certain experiments with that. I don't know what kind of control over the application of the field you have to create a sustaining burning plasma. We'll find out with Iter whenever that gets finished.
Right, the last one.
Correct.
And then you mentioned that these were neodymium yak.
Yes.
How do you get neodymium yak to operate at this point? I thought it was 1064.
We can tune the seed pulse slightly off of that fundamental frequency. We actually do that for the different cones, but it's all right around 1053 nanometer, plus or minus a few angstroms from that. And there's plasma coupling that takes the beams in and out of each other. But it's basically by tuning the seed pulse, you'll amplify only what you put in. So there are other research facilities that run on shorter timescales for that, the actual compression. But since you're generating X-rays, and like I said, I'm an engineer, I don't know the exact details of a short pulse. But you're trying to confine it by ablating a surface that has mass. It's going to have a velocity. So you have to do that for a certain amount of time. We do have a 4-beam petawatt laser in addition to this that takes one of the quads, chirp pulse amplification with gratings, and then compresses it down. Yeah, more or less. It's part of the NIF beam. It's used for diagnostics. There was an idea for fast ignition for a while, but that's kind of gone away.
But that is legitimately a strategy that some people think might work, which is you use the laser to do what we're already doing, and then if you maybe just at the right time, hit it with a femtosecond pulse, maybe you can initiate more fusion in one place that will drive the runaway. Yeah. So there are a lot of Japanese. I think the most research on that is in Japan.
Yeah, it's like right now we're a diesel engine. That could be like a spark plug, but right now the physics isn't there to support that approach.